In this video, we will discuss the fabrication of PV cell or photovoltaic cell. Photovoltaic cell is also commonly known as solar cell. What is a solar cell? It is a structure that converts solar energy directly to DC electric energy. Solar cell acts like a battery because it supplies DC power. If two differently contaminated semiconductor layers are combined, then a so-called p-n junction results on the boundary of the layers. By doping trivalent element, we get a p-type semiconductor with excess amount of holes. By doping pentavalent element, we get n-type semiconductor with excess amount of electrons. As the name indicates, photo means light, voltaic means volts. Photovoltaics is a method of generating electrical power by converting solar radiation into direct current electricity using semiconductors that exhibit the photovoltaic effect. What is photovoltaic effect? The photovoltaic effect is the creation of voltage or electric current in a material upon exposure to light. So, solar cell or photovoltaic cell or PV cell is basically a p-n junction diode where electrons will be produced when light impinges on it. So, current flows through the load. So, if you look at the definition of photovoltaic effect, it is going to be like this. The generation of voltage across the p-n junction in a semiconductor due to the absorption of light radiation is called photovoltaic effect. The devices based on this effect are called photovoltaic devices. Photovoltaic effect is the basis of photovoltaic power generation. When the sunlight or any other light is incident upon a material surface, the electrons present in the valence band absorb energy and being excited jump to the conduction band and become free electrons. These highly excited electrons jump into a different material, say electrodes. This generates an electromotive force or voltage, and thus some of the light energy is converted into electric energy, which means energy is generated in this way. Next we shall see briefly fabrication process of PV cell or solar cell. First step is refining silicon. The silica is reduced, that is oxygen removed, through a reaction with the carbon in the form of coal, charcoal, and heating to 1500 to 2000 degrees centigrade in an electrode arc furnace. So the basic equation is silicon dioxide plus carbon results silicon plus carbon dioxide. The resulting silicon is 98% pure. It contains iron, aluminum and boron. To remove these traces, further purification is done. In this, powdered silicon is reacted with anhydrous hydrochloric acid at 300 degrees centigrade to form SiHCl3. During this reaction, impurities such as iron, aluminum and boron react to form their respective halides. The SiHCl3 has a low boiling point of 31.8 degrees centigrade, and distillation is used to purify the SiHCl3 from the impurity halides. Finally, the pure SiHCl3 is reacted with hydrogen at 1100 degrees centigrade for approximately 200 to 300 hours to produce a very pure form of silicon. Above reaction takes place inside large vacuum chambers, and the silicon is deposited onto thin polysilicon rods to produce high purity polysilicon rods of diameter 150 to 200 millimeter. Based on the types of crystal used, solar cells can be classified as monocrystalline silicon cells, polycrystalline silicon cells, amorphous silicon cells. Monocrystalline silicon solar cells are made from a very pure type of silicon. More than purity, more efficient the material is. They are also the most space efficient. They also last the longest of all types. This superiority comes with the price tag. So you have to pay more for monocrystalline type solar cells. After getting the required silicon from the above mentioned chemical procedure, different methods of solar cells fabrication are applied. Each method involves doping of silicon to make p-n junction and the required processes to make a furnished solar cell. So this is the finished shell which is ready for encapsulation in a module. So this technology is called screen printed solar cell fabrication technology. Let us see briefly buried contact fabrication technology. In this we have the wafer before cleaning, wafer after cleaning, wafer with 100 nanometer oxide growth. So that is first oxide deposition, wafer after application of photoresist, thin photoresist application and first mask pattern transfer, wafer after development of first mask. So it shows the development of the first mask patterned wafer, wafer with the patterned oxide layer. So that is removal of SiO2 using buffered high frequency etching. Wafer after photoresist removal. So photoresist removal and KOH etching. Oxide removal with buffered HF. So we get a silicon wafer with KOH etching and the oxide layer removed. Next, ion implantation of N-dopant, that is phosphorus. Wafer after phosphorus and boron ion implantation. Next, we have growth of anti-reflective oxide layer. Wafer after second oxide growth. Next, photoresist application for rear contact. Removal of SiO2 using buffered HF etching from the rear side or back side. Removal of 2-inch wafer from 4-inch wafer. Next, thick photoresist application and a third mask pattern transfer. Wafer after third photoresist application. Aluminum deposition and lift off. Wafer after aluminum deposition. Final annealing step. So after annealing, we have the final solar cell. Recent fabrication researches. So the fabrication fabrication technology of solar cells are evolving, mainly to increase the efficiencies of solar cells. So to further increase efficiencies of solar cells, it is found useful to modify the structures of solar cell to maximize the life of cells as well as to increase their power rating. So many fabric that solar cell technologies are evolving, and The nanotechnology is also one among them. Thank you.